All right. Ladies and gentlemen, class recording has started. So, on Monday, we introduced the ideas of force and then topics that go along with those ideas of force of Newton's laws. So first, as far as a force, how did we define force? What is a force? Force is a push or a pull, right? In a direction, meaning that it is a vector quantity that will become important here in a little while when we start doing some of these problems, okay? But more importantly than what force is what force does, right? What did we say that forces cause?
A reaction.
Acceleration, right? Forces cause acceleration. They cause things to speed up, slow down, or change directions, or some combination of those three, okay? After we introduced the ideas of force, we went in and talked about some of the key concepts, right? First key concept, talked about Newton's laws. First key concept is Newton's first law. Newton's first law gets summarized with one word, right? What is that one word? Inertia. Inertia being that tendency of an object to maintain whatever it is currently doing. If it is moving, it will continue to move with a constant velocity. That means straight line, same speed. If it's at rest, it will maintain being rest unless it is forced to do so, right? By a quote-unquote net force, right? Where we look at the sum of all forces, the combined effect of all the forces. Newton's first law deals with things staying the same, inertia. Newton's second law deals with acceleration. The acceleration of an object is affected by two things. Do we remember what the two things the acceleration of an object is affected by or determined by? What are the two things that affect acceleration? Well, that is acceleration. Say again? There's two factors that determine the acceleration of an object, or that affect how much acceleration it has. Net force is one, and then mass. The acceleration of the object is dependent upon the force that is acting on that object and the mass of that object. And that all those contributors get summarized in this equation, sigma F is equal to m times a. We talked about Newton's third law, which we summarized with the phrase action-reaction. We said that forces can't exist in isolation. They have to be accompanied by something else. That if I push on something, it pushes back on me just as hard, but in the opposite direction. Okay, so now that we've gone over those topics, let's go over a couple of problems. Let's start putting some numbers into these ideas. The first couple problems that we do are pretty straightforward and pretty simple. They're meant to be. We're going to build up, all right? If you think I'm going pretty slow, and if you think that I'm being very, describing things, being over-descriptive, I am at the beginning. If you understand it and you see where it's going, great, no problem, all right? But I want to make sure we at least talk about why things are called the way they are, why things are written the way they are, et cetera, et cetera, et cetera, okay? So, with that being said, we are going to start on those two sheets with this one here. It says number 4. What force must be exerted on a 1,500 kilogram car to make it move with an acceleration of 3.8 meters per second squared? First things first, what is this question asking us for? Force, right? What force? So that means that force is our unknown in this problem, okay? Oh, by the way, sorry. This problem that we're doing right now, there's a second problem that I forgot to copy on there, so you might want to leave a little bit of room so that you have space to do the second problem as well, okay? All right, things that we know about this car. What did it tell us about the car? Okay, the 1,500 kilograms, right? That's a mass. So the mass of this car, 1,500 kilograms. And then, what else did it tell us about this car? It is accelerating at a rate of 3.8 meters per second squared. Okay? So, numerically, when we start looking at quantitative values or numerical values that go along with forces, almost always it comes back to Newton's second law, that sigma F is equal to m times A. Now, we said the sigma represents what? The total or the sum. In this case, how many forces have they mentioned in this problem? Well, this one that they want us to find, right? But just this one. So, in this case, we're just going to put F in there for sigma F. Because if there's only one force, the sum is just the value of that force, right? Then, we plug in the mass, right? 1,500 kilograms. And then the acceleration, 3.8 meters per second squared. Okay? So you take it to your calculator, you multiply the numbers, and I think you end up with 5,700. Is that correct? Okay. But from a unit standpoint, right, we got kilograms here, we got meters per second squared here, nothing cancels out, so we have to keep all those units. The combination of those units ends up looking like this. Okay? Kilograms times meters over second squared. That's just the conglomeration of all these units, right? But we talked about on Monday that this combination of units, kilograms times meters over second squared, we represent that with the capital letter N. So the answer to this question is 5,700 newtons, right? That combination of units, kilograms times meters over second squared, is the combination that we use to represent units, or sorry, newtons. Okay? Good there? Next question. Next question is one that this doesn't appear on your sheet, so we're just going to go through it up here. This is on page 181 of your book, which is the end of chapter 5. Okay? But number 60, it says, on an aircraft carrier, a jet can be catapulted from 0 to 250 kilometers per hour in 2.00 seconds. If the average force exerted on the catapult is 9.35 times 10 to the third, what is the mass of the jet? So, first things first, this question is asking us for mass, right? What is the mass? Means that m equals question mark, right? All right, things they gave us. Average force exerted by the catapult is 9.35 times 10 to the third. So force is 9,350 newtons. All I did was turn this number in scientific notation back into decimal notation. Okay? And then it gave us a little bit more information, right? It told us that this jet is catapulted over a time frame of 2 seconds, and that it goes from here to here. But if we look at the unit, right, kilometers per hour, that's a unit of distance over a unit of time. What kind of measurements are these? Those aren't accelerations. They are what? They are velocities, right? Distance over time is a velocity, okay? So it gave us the initial velocity, right? That being 0, and then it told us that the final velocity is 250 kilometers for every 1 hour, right? So first, before we do anything, do we want this unit in kilometers per hour? No, right? Meters per second. So I'm just going to do a little conversion, right? 1 kilometer on the bottom, 1,000 meters on the top, right? And then 1 hour on the top here, 3,600 seconds on the bottom. I'm not necessarily going to, I won't ask you to do that on the quiz, but all I did was to convert my kilometers per hour into meters per second. Sam, have you figured out the kilometer or the meters per second value yet?
69.44.
So 69.4 is that velocity in meters per second. Okay? Now, right, Joe, you said that originally you kind of mentioned that these were accelerations, right? Because that's convenient if we have acceleration, right? Because we use Newton's second law, right? And Newton's second law has mass in it. If we know the net force and we know the acceleration, we could figure out the mass, right? But do we know the acceleration? Wasn't given to us in the problem, but they did give us the time and the initial velocity and the final velocity. If we know those three things, can we figure out the acceleration? Yep, right? There's couple different ways you can do it, but if we go and we use a kinematic equation, right? Vf is equal to Vi plus a times t. Not the only way you can figure out the acceleration, but one way. So we figured out that Vf was 69.4. Vi was 0. We don't know the acceleration. We want to find that so we can use Newton's second law, and at the time was 2.00. And when you do that, what is it? 34.7 meters per second squared. Now that we know that acceleration value, can we figure out what the mass is? We can, right? We found out earlier on that this force was 9350 newtons, right? Equal to the mass, which we don't know, but we did just figure out the acceleration was 34.7 meters per second squared. If I remember right, 269.45. And then if we round that for sig digs, 3 sig digs, 269 kilograms. Good there so far?
Will we do one like this on the quiz?
This one's possibility of doing one like this on the quiz. Sam, this one actually is more important for you to complete your lab later today. That's why I wanted to do an example like this so that we could, figure out what that is. Okay. All right. Next, go to that one example problem that's down at the bottom about 3 guys pushing a boat named Mo, Larry, and Curly.
Wow.
I'm sure that's just random names they picked, All right, so it says, Mo, Larry, and Curly push on a 752 kilogram boat that floats next to a dock. They each exert an 80.5 Newton force parallel to the dock. So part A says, what is the boat's acceleration if they all push in the same direction? So for part A, it wants to know what the acceleration is, right? It told us that the boat has a mass of 752 kilograms. And then it also told us indirectly, although if you look at the picture you can figure it out too, that there are 3 forces that are acting on that boat. Up until the 2 problems we've done so far, there's only been 1 force, so we just kind of went with that. But here there are 3 forces. If there are multiple forces that are acting on an object, this is what we do. We generally represent them all with F, except you can't have 3 F's, right? So we have to distinguish one from the other. So we usually use a subscript to distinguish one from the other to the other. So this would be the force of Mo, this would be the force of Larry, this would be the force of Curly, right? We use those subscripts to distinguish this one from that one from that one, okay? it tells you in the problem that they all push with an 80.5 Newton force, right? So we know that all of these forces are 80.5 newtons. But earlier in the period and earlier this week, we introduced the idea that force is a vector quantity, right? Meaning that it has to have what? Direction along with that magnitude. Underneath the picture, they set up a frame of reference. They called the back of the boat the 0 point, and then they put an arrow facing towards the right. I wish they would label this arrow as positive x, but they just label it as x. But they're telling you which way is going to be the positive direction and which way is going to be the negative direction. So in part A, when all of them are pushing this way, which direction are they all pushing in? Positive direction. So all of these forces really aren't 80.5 newtons, they're actually positive 80.5 newtons. Now, at this point, mathematically, it's not going to make a big difference, but in the next problem, it will make a big difference. So, if we want to know acceleration, right, Newton's second law tells us that the acceleration of an object is dependent on two things: the net force acting on that object and the mass of that object. Now, the net force idea, right? We said that what does the net force mean, or what does the sigma tell us? Total, right? Or mathematically, what are we going to do? Add all of them up. So, in this case, there are three forces. So if we change the left-hand side of this equation, or we can change the left-hand side of this equation to look like this. All I did was just add up the three forces that are acting on that boat. The right-hand side of the equation remains exactly the same. Do we see how this is the same thing as sigma f, right? The three added together. Okay? Now, the way I'm going to write it this time, you might think is unnecessary. But I'm going to tell you why I'm going to write it this way now, and why I want to write it this way, especially important for the next part. Okay? So now we start plugging in things that we know. We know that Mohs force is positive 80.5 newtons. And then we add that to Larry's force, which is positive 80.5 newtons. And then we add that to Curly's force, which is also positive 80.5 newtons. We know that the mass of the boat is 752 kilograms, and then A is the only unknown here. Okay? The reason why I'm writing it out this way is the following. These addition signs that I have highlighted in yellow, those are part of the equation. You can't get rid of those. Those addition signs go along with this sigma idea, right? We're adding all of the forces together. These addition signs here, here, and here, those aren't representing addition. What are those representing? The direction, right? So those positive signs inside the parentheses could change depending on the direction. But the positive signs in between the parentheses have to remain the same, because that's what sigma means. That's what the sum means. So in this case, because they're all positive, right, mathematically, what are we just going to do with these three numbers? Add them all together, right? Once you add them all together, you divide that value by 752, and then you can get your acceleration of that boat. Anybody run that through yet?
Yeah.
What'd you get?
0.321 meters per second squared.
And that's going to be positive, right? All right, good there? Questions with that? Good. Okay. Part B. Oh, crud. Stand by. Thought I fixed this, but apparently not. All right. For part B, first off, I'm going to get rid of all this writing. Okay. Now, for part B. Again, part B wants to know what is the boat's acceleration. So, A is still our unknown. But now it's saying that Larry and Curly are going to push in the opposite direction from Mo. The mass of the boat still remains 752. That doesn't change. And there are still three forces. One from Mo, one from Larry, and one from Curly. Mo's force is still going to stay positive 80.5. And it says that Larry and Curly push in the opposite direction. That doesn't say anything about how hard they push. They still push at 80.5 newtons, but if they push in the opposite direction, how are we going to distinguish that from the way that Mo is pushing? Make that negative, all right? Finding the acceleration of this boat still depends on the net force and the mass. But now, right, force of Mo plus force of Larry plus force of Curly equals m times a. Now when we start plugging things in, those addition or those plus and minuses become very important. Remember, this plus sign and this plus sign, the two that are highlighted in yellow, those have to stay plus signs. They go along with the sigma, right? Sigma means add. So those plus signs go along with the sigma. But this, and this, those are telling us the direction of those forces. Those can change. So, you plug that through your calculator, and you should end up with negative 0.18.
107.
Oh, 107, you're right. Okay.
Sorry.
It's all right. Calculator okay?
Yeah.
All right, do we get that? Some clarification on the answer. First, this came out as a negative acceleration, right? Does that mean the boat is slowing down? Not necessarily, right? In this case, if the boat is floating next to the dock, without saying that, they are implying that the boat is at rest. If something is at rest and experiences a negative acceleration, what's actually going to happen to it? It's going to go backwards, and it's actually going to do what while it's going backwards? It's going to speed up while it's going backwards. If it starts at rest, even though it has a negative acceleration, that means it's going to speed up just in the negative direction. Okay? Good there? All right. Let's do one more. The remainder of that page, the two problems that were, the one problem that's down at the bottom of that side, and then the two that are on the back, very similar to those two examples that we just did. Multiple forces acting on an object, making sure that we're taking care of the net force, right? Sigma F, positives, negatives, take care of those, okay? Next problem I want to do for you guys is on the next sheet that's called Tippy Canoe. It's catchy, isn't it? So Tippecanoe says that there are two groups of canoeists. We had a discussion in one of my previous classes that if that was actually what you called people who were canoeing, if they were canoeists or canoers or canoeites. That was another one that we thought of.
What is it?
I don't know. Don't really know. So maybe we can do that after the problem. We'll Google this and find out what do you call a group of canoers. We thought that it'd probably just be most accurate to call them
Two groups of canoeists.
canoeists. Well, that's what it says here, but that
You asked for a group of canoers, it's a group of canoeists.
we thought it would just be better to call them canoe enthusiasts, because yeah, I mean look at these people, right? I mean, do they not look enthusiastic? I think so.
This is everyone on YouTube's entertainment right now.
All right, so two groups of canoeists or canoers or canoeites meet in the middle of a lake. After a brief visit from a person in canoe 1, or after a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is 150 kilograms. Mass of canoe 2, 250 kilograms. What is the acceleration of each canoe? So, in this problem, we actually have two unknowns, right? We have the acceleration of canoe 2 and the acceleration of canoe 1. The acceleration of each canoe. So, just in the general math sense, if we have two unknowns, how many equations are we going to need to have? Two equations, okay? All right, let's start things we know. It tells us in the problem that the mass of canoe 1 is 150 kilograms. And then it tells us that the mass of canoe 2, 250 kilograms. And then it says that canoe 1 pushes on canoe 2. So, there's a force of canoe 1 pushing on canoe 2. That isn't necessarily always how the book or other people note that, but it's important in this problem that 1 is pushing on 2, so that's why it goes in this column over here, right? And it tells us that that force is 46 newtons, right? But also, if you look at the picture, they have set us up a frame of reference, right? Here's the reference point, and they have the arrow pointing towards the right, this being the positive x direction. So if 1 is pushing on 2, which direction is that force going to be acting on canoe 2? Positive direction, according to this frame of reference. Okay? Do we have enough information to figure out the acceleration on canoe 2 right now? We do. So we can go Newton's second law, right? There is no mention of any other forces, even though in reality there are quite a few other forces, but they don't really mention anything else in this problem. So we'll just go that the force of 1 pushing on 2 is going to be our only force, so that's the net force. And then mass of 2 times acceleration of 2. We said that this is going to be positive 46 newtons. The mass of canoe 2 is 250. So we can solve for the acceleration. And when you do, you end up with, that was the 0.184. Okay? Good there. Do we have enough information to find the acceleration of canoe 1 yet?
Yeah.
Well, yes, but not quite directly, right? In order to find acceleration, we need to know mass and we need to know net force. But do we know anything about the forces on canoe 1? Okay, kind of. We said that Newton's third law tells you that if canoe 1 applies a force on canoe 2, automatically equal and opposite reaction canoe 2 pushes back on canoe 1. So there is a force of canoe 2 pushing back on canoe 1. Newton's third law says those forces are equal and opposite. So they're 46 newtons in magnitude, but if it's opposite, what does that mean? It's going to be in the negative direction. So once again, we do Newton's second law, but now we're just looking at canoe 1. Negative 46 for the force, 150 for the mass. Point 3. What did they send it to? Okay, good with those two values. So, a couple of things before we wrap this up. Okay, first, one positive acceleration, one negative acceleration. Does that mean one is speeding up and one is slowing down?
No.
Not in this case. They both start at rest, right? After a brief visit, we'll assume that that means that they start at rest. Okay? In both cases, these objects are speeding up. One speeds up to the right, one speeds up to the left. Okay? Joe, to answer your question from before, right? In this case, which one is actually going to be going faster?
One, or one on the left.
One on the left, canoe 1, right? Even though it tells us in the problem that canoe 1 pushes on canoe 2. But we find out that even though 1 pushes on 2, in actuality, 1 ends up going faster, just in the opposite direction. Even though they experienced the same amount of force, was their resulting motion the same?
No.
Because why? Because the mass differs, right? For example, right, if you stand on the ground and you jump up, you push on the earth. That's how you start jumping. And the earth pushes back on you, and you go up. Does the earth go down? Well, I mean, obviously, you know. Does the earth accelerate downward because you accelerated upward? What were you going to say, Morgan?
Instead of doing this, couldn't we just take the fraction from these and then like times it?
In this case, we can. We could set this up as like a ratio,
Yeah.
okay? Although the only problem with setting up it as a ratio is technically these two forces are not the same, right?
Okay.
Because why?
So we'd have to make one of them negative.
If you knew that, okay, it has to be the opposite
Yeah.
direction, you could solve it that way because you could use the...
But we'd get credit if we did it that way?
Yeah, I would give you credit for that as long as you realized, hey, this has to be a negative force, like I would be okay with that, okay? Back to the question, right? When you jump up, does the earth go down?
Well, I mean,
Yes.
maybe does.
It doesn't, but like it's supposed to.
Okay? You and the earth feel the same force, right? But
Kind of does.
how much mass does the earth have? A lot more than you, right? So does it accelerate? Okay. So question is, does it accelerate? Yeah. Is it a lot? No. So the next question that comes up is, well, how much? Okay. There's another question that somebody's thinking right
How much
now.
does the Earth weigh?
Well, I know how much the Earth weighs, and we could calculate how much the Earth's acceleration is, but there's another question that somebody's thinking right now.
How heavy the person jumping is.
Okay,
How much
yeah.
force did he use to push down?
Okay, we could figure that out. But then, even with that amount of force, even if Joe jumps, right? Okay, the mass of the Earth is so large that its acceleration is super, super small.
Doesn't it add up?
So the question that then comes up is,
What does that mean?
there's another question I was thinking.
What's the effect? What could happen?
There we go, Sam. Sam says, here, sorry. Oh, I mean, it's been recording, so So I gotta finish this discussion now, because if somebody was watching it, they'd be like, you know. What if everybody jumps at the same time
In the whole world?
in the whole world, right?
All the forces would cancel.
Ah,
We'd all go through the ground.
okay. So here's the Earth, right? So if we're over here, standing on this side of the Earth, not to scale, okay? You push on the Earth, you apply a force to the Earth, okay? And then the Earth applies a force on you, so you go up and the Earth goes down, or you go to the right and the Earth goes to the left. But if there's somebody over here, not to scale, right? And they push on the Earth,
Like his head.
yeah, his head didn't turn out so hot. They push on the Earth this way, the Earth pushes back on them this way. Okay? They go up, the Earth goes down. But what about these two forces?
Cancel each other.
They cancel each other out. So everybody jumping at the same time doesn't really do us any good.
We have to be
Won't there be some
in
from-
one
Unless
we're all in the same spot.
if we all go somewhere in the same spot, right? The North Pole, or well, the North Pole is like starting to melt now, so probably shouldn't go there. Yeah, yeah. We could go to Australia, like everybody meet in Australia, you know. So, okay. The answer is I don't know. I've never figured it out before. So
You thought about it?
every year,
Really?
yeah.
Does it keep you up at night?
No. so,
Everyone decided experiment.
so I mean, yeah, Red Bull, yeah.
Get sponsored.
So it gets man. So,
Fly everybody out to Australia.
man, that could be like your senior project, Sam. I feel like, get Red Bull to sponsor the Great Physics Jump. So, I mean, they've already sponsored one physics jump. Why not this one? I mean,
What if we spiraled out of control?
you know, the guy that jumped out of space. You know, so. All right. So on that sheet that we were just looking at, other problems on that sheet similar to the one that we just did. Okay. So quiz tomorrow over Newton's Newton's second law, third law, problems, and calculations. Okay.